This is a short video demonstrating the optimal CSMA. We went all the way from the mathematics of stochastic approximation theory to deployment over off-the-shelf Wi-Fi radios. The central question here is to decide who can talk at each time slot in an interference environment, and do so distributedly through random access protocols. The performance benchmark can be captured in a utility maximization formulation that implicitly assumes a centralized control. The key challenge is script S, the set of feasible schedules. In our actual design for adaptive CSMA, the degrees of freedom are the contention aggressiveness, Poisson rate lambda, and channel holding time, drawn from exponential distribution mu. In the algorithm, each link L distributedly updates an internal counter Q based on the service rate D received over the last time slot, and its own utility function U, with algorithmic parameters V and B. Then the ratio between lambda and mu is adjusted to be equal to exponentiated Q in the next time slot. This simple algorithm can be proven to converge to an approximation of the original utility maximization benchmarking problem, and the approximation error term can be made arbitrarily small. We did not stop at theory, but continued to implement it on top of conventional hardware. In the process, we also discovered, quantified, and bridged the gaps between the theory and practice of wireless scheduling. The implementation ran as a shim layer overlaying on top of 802.11 Wi-Fi driver. The hardware platform is standard netbooks. Each netbook has two PCIe interfaces, allowing us to have two independent Wi-Fi interfaces. One is 802.11a card for data channel, and the other 802.11n card for control channel. This minimizes measurement errors. When installed Linux kernel 2.6.31 for OS, and Met Wi-Fi and F9K device drivers for .11a and .11n interfaces respectively. We use the Common Code architecture, a code reuse platform that translates a simulation code directly to real experiment without code modification. The hardware adapter in Common Code enables the packet transmissions. There are many interference scenarios that we tested oCSMA against, including the four atomic topologies: fully interfered, hidden terminal, information asymmetry, and flow in the middle. We pick one of them, flow in the middle, in this short video. The packets are queued up to the maximum buffer size of 200 packets. The default contention window size is 16. In 802.11 DCF implementation of static CSMA, the middle flow cannot have sufficient opportunities to grab the channel, leading to starvation. This is confirmed in our experiment. By measuring both the instantaneous and average throughput, we see that the middle flow receives very little throughput. In contrast, oCSMA provides the first theory-driven and experimentally verified solution to this well-known problem in Wi-Fi. All transmitters adapt contention window values based on their Q length. As Q length increases for the middle flow and decreases for the two side flows, the middle flow gets more aggressive and side flows less so. The resulting throughput distribution is a lot more fair. If proportional fairness is used through a log utility function for each node, the throughputs for the three flows should ideally be 2:1:2 ratio, and that's what oCSMA achieves indeed. There are many more interesting observations from our experiments, including major discrepancies between theory's prediction and experiments data. We invite you to take a look at our recent papers. Generally speaking, the biggest gap between theory and simulation is the presence of collision. The biggest gap between the simulation and clean slate implementation is the complicated ways interference happens, SIR-based receiving with capture and imperfect sensing. And the biggest gap between clean slate and legacy implementation is the design constraints in Wi-Fi, including its asynchronous transmission and back-off granularity. In identifying and bridging these gaps, we're further refining oCSMA's original theory and are obtaining even more encouraging results. This completes the loop that started from modeling realities as mathematical crystallization, to theory, to implementation, to empirical data collection, and back to stronger and more relevant theory. Implementing and refining oCSMA is a joint effort by KAIST, Rice, and Princeton, and funded by Air Force OSR, Muri, and NSF NETS grants.